Hi everybody. I'm Hirofumi Hashimoto from California State University, Monterey Bay, and I'm a contractor at NASA Ames Research Center NEX group. Today I would like to introduce my new data set which I made recently. And today's title is High Resolution Mapping of Daily Climate Variables by Aggregating Multiple Spatial Datasets with Random Forest Algorithm. This is an example of an existing gridded climate dataset. There are reanalysis data, like analysis data, radiation data, precipitation data, gridded climate data, and other satellite products. This is just an example, so there are more other data sets. So most of the data starting from 1980, and then my data set is also starting in 1980. So why do I need a new data set is the question. So if we classify the gridded data, gridded run surface data, there's so many ways to classify, and depend on the variable time step, time range, resolution, graphical region, method, and the input data. For example, variable temperature, precipitation, humidity, wind, radiation. Like in the previous the figure, I show many data sets, but except for the analysis data, most of the data doesn't have all of the variables. And then time step can be hourly, daily, monthly, and the time range can be from 1998 to current, real-time data. So resolution can be so geographical region, North America corners, and the method can be physical model, just satellite model, and the statistical model. And the input data can be satellite, radar, elevation, whatever. So if we pick one each of them, we have many, but the combination of these can be the possibility we need the data is very few. For example, the ecosystem model we use mainly for prism or Daily data because it has many other variables and it's very stable. So we want to create the other data set using a statistical model. So we call this data set is NEX-GDM, NASA Earth Exchange Grid Daily Meteorology. And the data is daily climate data, and the resolution is 1 kilometer, and the time range is from 1979 to 2017 for now. And the geographical region is corners. And the variables is precipitation, maximum temperature, minimum temperature, dew point temperature, wind speed, shortwave radiation. These variables can be useful for ecosystem modeling. So method I use as I pick up random forest. It's one of machine learning technique. And the most big feature of this NEX-GDM is I use a lot of data sets, including 30 spatial data sets plus 2 ground observation data set. So objectives of this study is first, creating gridded data set using multiple time variant spatially continuous data set for ecosystem modeling. And second is proposing straightforward methodology to apply machine learning algorithm to interpolate ground observation data into spatial maps at the continental scale. The third is testing whether NEX-GDM accurately captures the spatial variability of those climate variables. At first, I want to explain the random forest, but this is for the young scientists. I'm sure you guys know very well. There are many ways to explain random forest, but I like this way. The random forest is a decision tree plus bugging plus a random selection of predictor. So this curve is a true curve. This is an example of, and I would choose just a single variable as an example. Then it's a observed data should have the error, so we can get those dotted data in the reality. And if we have, so the random forest is a decision tree based on. So if we use a decision tree for one decision tree, we can get like this. So we don't like these for overfitting. So that is the purpose of random forest. So random forest actually pick up 2/3 of the input data. I mean, 2/3 of the sample data. For example, this is green dot is 2/3 of all the sample data, and apply the decision tree. And second, again, pick up the 2/3 of the sample and the calculator the decision tree same way. This is called a bagging actually. At the end, we can get the mean of those lines, decision tree lines. Now again, also random forest apply for the decision tree the random selection of the predictor for each split of the decision tree. Then we can get we can avoid the overfitting. So this is the random forest concept. So now I'm explaining the input data. So for this NEX-GDM, I use the following data set. Number one, reanalysis data, NCEP NCAR reanalysis 2.5 degree axis-error, NCEP reanalysis 2, and CFSR, MELA2, NAR. NAR is not a global data, but it's covered CONUS region. The other is satellite data. I just pick those satellite data. GridSat B1 is a geostationary data, geostationary satellite data set, and the Trine 3D 42 version 7, and the Terra MODIS data, Aqua MODIS, LTDR, GIMS 3G. I just pick up by after. So even each satellite, even each sensor, I pick sometimes 2 or 3 data sets, 3 or product. For example, for precipitation after 2000, data increases rapidly, and temperature gradually increases the number of stations. Same way, but the number is very small compared to temperature of precipitation. Those, especially for solar radiation, is very few. There is a small number of stations available. So from now, I want to explain how to apply the random forest to spatial data. So I call the methodology as AINA, aggregated and incorporation of NEX archives. Okay, so first I create a grid of the point for random forest. So every 20 kilometers, I want to make a random forest. Then for each random forest, I pick up this case 200 observation, nearest 200 observation at every 20 kilometers. So I find the closest point, then pick up the data as the exact point for each station, then make a database, and I get the point value of all the spatial input data at the weather station. So these spatial data is satellite reanalysis, etc. I explained before. Then calculate a random forest using this database for each grid. Then at the end, I want to estimate each point. This case, a 1 kilometer grid. This is 20 kilometer grid, and calculate the surrounding 16 grid, and then weighted average of the estimate from each of the grid. The weighted average is the final estimate. This is the way how I calculate for this data set. Estimate the data set As you can see, there's no, you cannot see any grid or any artificial lines here.
Oh, what is it here?
This is a difference of NEX-GDM with USHCN. This is a USHCN data is this point data, and then compared with the prism and the Daily data set. It depends on place, is overestimation, underestimation, of course. So this is a precipitation data set. And then next is minimum temperature, the same way compared to USHCN and the prism and the Daily. So you can see the NEX-GDM to some extent overestimate compared to prism and Daily, but not so much with compared to USHCN. The daily comparison. The previous one is a climatology comparison of climatology. This is just a 1 day comparison, how the data looks like. And this is daily precipitation on 1994, on July 3rd, when the tropical storm Alberto hit the southeast US for NEX-GDM and the prism and Daily. So here you can see that the Daily is very more smooth data. And you can see prism there are some very dots, and NEX-GDM are kind of middle of this data set. The daily minimum temperature on 2006, July 22, when the North American heat wave hit California, NEX-GDM, prism, and a Daily. And these are very similar. It's hard to find the difference. Maybe big difference is maybe California, Central Valley, yes. And like that same way, Daily is more smooth. Then this comparison with Amarflux data. So no, as far as I know, those three data use Amarflux data for the data. I mean for input data. So Amarflux data can be used for the kind of validation. So just for simply, just I compare using the statistics of R square RMC bias for each variable. So NEX-GDM is doing well, and yeah, similar value for compare with the prism data. A little bit better in prism data, yeah. So this is a summary for the Amarflux data. So the Daily uses, the short variation from Daily is can calculate from those temperature data. So it's not simple interpolation data compared to precipitation temperature. That is the reason I think. But in my case, I use this interpolated from the station data. That's why I have high correlation. And so the next one is a variable importance, which input is contributing to estimation. So this is a special pattern of annual mean importance of input data for precipitation of 2009. And I pick up the 9 input data set of highest average importance. So it's hard to see. This is stage 2 data. This is for precipitation. So the radar data, stage 2 has high contribution, especially for the east corners. Then there is the reanalysis data and the grid start, geostationary satellite data, same on grid start. And again, reanalysis data, again reanalysis. So those reanalysis data show a very similar pattern But this radar is very high contribution to the west part. Then the high elevation in the high elevation region, the G-top elevation data has high contribution to the models because of the Hashimoto also elevation effect on the precipitation. The next one is the Tmax contribution for its data. In this case, CFSR reanalysis data and NAR reanalysis data. Then the G-top elevation has a high elevation. So this G-top has a high contribution to the mountainous region. Then the analysis data, and here the MODIS 11 runs surface temperature data. They contribute most of the time the western part. This case is a T-mean, the same way. But here is LST has, this time nighttime LST has a more contribution compared to T-max. Then the other are the analysis data. And the G-top is not contributed to very much compared to T-max. Then this is how how satellite data can contribute to the method, to the models. I just use this case. This case I run the model with a full run, and this one I use without satellite data. And this is a station observation, which commercial data actually for the Earth network. So I didn't use this data as input. And then this is NDVI. Yeah, this is actually New York. And the elevation data. So if I didn't use the satellite data, you can see this data is close to the elevation data. So elevation data has much contribution, but this doesn't match well with the station observation data. So that means that I need satellite data to estimate those regions. Then I made summary for this same region with satellite data and without satellite data. I put more data here with satellite data. So you can see that this case nighttime LST has big contribution. So this means this shows the importance of satellite data for this data set. Then finally the limitation of the use of NEX-GDM. The problem is these are the limitation to use this. And the first one is analysis of extreme event or region. So ionized regression is based on decision tree algorithm. So the range of NEX-GDM is within the maximum and the minimum of station data. Therefore, NEX-GDM may not be suitable for analysis of climate extremes. The second one is long-term trend analysis. So there are no factors which can influence the long-term trend. The first one is artificial trends of weather station data, and the second is change in density of weather station. The final one, third is very specific this data set, the discontinuity of input data, because we put a lot of data compared to the other data set. So for now, just I can say the further study is required for discussing long-term trend using NEX-GDM. The scalability is, because I know it's a statistics model, NEX-GDM can be easily scalable. Time range, I can run the near real-time processing. Time set to hourly is easy also. I can change the resolution to really high resolution. With the highest resolution of input data. Then geographic region, any region is of course is okay. I can put a more variable. Example, snow depth, wind direction. So in the future, we will produce the other climate variable taking advantage of the scalability of in a framework. Conclusion. We created the NEX-GDM dataset by applying INA framework to the conterminous used to produce high-resolution climate field from 1979 to 2017. Statistics from a comparison with existing dataset produced with completely different algorithms show that the accuracy of NEX-GDM is comparable with those data and useful for ecosystem modeling. We quantified through the variable importance analysis the importance of the contribution of satellite data which are not used by other grid climate data product to the NEX-GDM. So the NEX-GDM dataset will be available on the NEX facility. Thank you for listening.